Hello and welcome to a new video in the video series on systems biology, digital twins and AI. So we are still in block 1 on TBMT 42, which means that we are still learning how to formulate models. And in this particular video, we will look at so-called lumped parameter models, which appears when you simulate blood flow. And then you again use the analogy of an electrical circuit, but here it's actually not electrical, but analogous to an electric circuit. And this will allow us to write up the differential equations, but this time they might not always be ordinary. Sometimes they might be differential algebraic equations. So if you cannot solve for x prime and write it out explicitly to the left-hand side, then you have to write it in this form instead. And it is slightly more general and slightly more difficult to handle type of equations. So that's the challenge, how to go from here to here. So blood flow models. The full version is to simulate this type of three-dimensional time-varying flows, which involves solving the Navier-Stokes equation. This is based on partial differential equations and gives time-varying three-dimensional simulations, as seen in this animation here. You can do that using software such as Phoenix. But the problem with this, that means, which is why we don't advocate it as a central thing in this particular course, is that it's hard to estimate parameters using this approach, because it takes a long time, maybe hours, maybe even days or weeks, to just do a single simulation. And when you do optimization, you need to do thousands and thousands of simulations. So therefore, you study simpler models. And the one that we'll look at today is the one called the lumped parameter models, or zero-dimensional models. So zero-dimensional because they have no partial derivative left, except for the time variation. And either they are ODE or they are DIE models. And again, this builds on something called the hydraulic analogy, which reuses concepts from electronics to understand blood flow. And this is an analogy that gives reasonable equations. It shouldn't be taken too literally. And let's, well, we will get into this when we get into the details. But the basic idea is that you have some kind of blood flow here in a blood vessel. And in electronics, you have a flow of charged particles. In the beginning of electronics, you actually believed that there was some kind of fluid that was flowing before you understood about charged particles. And electrons and so on. But the idea is that these are sort of corresponding concepts. And furthermore, what drives blood flow is that you have higher pressure over here than here. And that is basically what is driving the flow. So it's the difference in the pressure that drives the flow. And in the same way, what makes charged particles flow is that the potential, the electric potential, is different here from here, and that makes the charged particles move in one or the other direction. And this difference in potential, this is of course the voltage when you talk about electric circuits. So the analogy here is that voltage corresponds to the pressure difference. And as you see here, there might also be some places where it's harder to flow. There, for some reason, there is more resistance to the flow. Maybe it's too narrow to be able to flow freely. and therefore this will be a sort of blockage that will mean that the flow that is the same all over the place here will be limited by this resistance that we have here. And in the same way, of course, in an electric circuit, you have some resistance everywhere. You have some resistance everywhere here as well, but you might have certain places where you have a well-defined resistance that is higher and so high that you need to sort of take it into account as a special section, so to say. So these are sort of the basic analogies, you can say. So now let's look at these component equations. So we already looked at the resistor, and here Ohm's law just carries over directly. So we already saw that the voltage corresponds to pressure difference, flow corresponds to current, and resistance is resistance. It's called resistance here as well. So blood flows with a certain speed that depends on the resistance R to the blood flow. The higher the resistance, the slower or lower the flow for a given pressure difference. Okay, so here, this is very straightforward. The next one is a little bit more strained, maybe. So here we have an inductor. And an inductor is something that can appear in electric circuits. If you have this sort of coil, then that can lead to certain properties because of the way the Maxwell's equations relate to electric and magnetic fields. And of course, there is no Maxwell equation here because you don't have these two orthogonal fields. But the same properties as appears in inductor is something that you might have sometimes when you have blood flow. And that is that, as we see here in the equation, changes to the flow, they are associated to an appearance of a voltage or a pressure drop across this unit here. So they don't appear if the IDT is 0, then there is no voltage across here, but and no pressure drop. But if you have changes, then you see these things. The analogy here is to sort of say that this inductance L, which describes the property of this coil or the inductor, that is translated as inertance of the blood flow. So blood flow changes are met with an inertance L, which counters that change, which means that there is sort of a resistance to change, you could say, which as long as there is a change ongoing, this resistance will prevail, so to say. But so it's the same as when you have a physical object that you want to accelerate. It has an inertia. It has a sort of resistance. It doesn't accelerate automatically, or in no type. There's sort of resistance to that. So it's the same type of resistance, but it's not the resistance to the flow. It's the resistance to the change of the flow. So these equations are identical, you see here. The only difference is that it's the derivative of the flow. Okay, so the final thing is that you can have the final thing that we'll take up now here. There are more things that you can introduce as well, but these are the things that we'll consider now in this video. Is the capacitor. So a pressure change. So you have pressure difference, and if that is changing, so you sort of have the sort of incentive to have a bigger flow or a smaller flow. There is again a sort of transient phenomenon that will temporarily be stored up in the capacitor. if you have an electric circuit. So this will build up more charge here or less charge, depending on the direction of the change. And in the same way, if you have a blood flow that sort of wants to increase, so to say, because the pressure difference has changed, then if there is a compliance of the walls, if they can sort of adjust, if they have some flexibility, then the sort of ballooning can happen. And this is again a sort of temporary local flow, which is just the expansion of the blood vessel. So this is sort of analogous to the storing more charge in the capacitor, is sort of doing this ballooning effect. And here, so the sort of, this is maybe more analogous, you could say, or more that you can carry it over directly. This sort of interpretation, you could say. Okay, so this here will be the conductance and the compliance. So this final thing is called the balloon effect or the Wind-Kessel effect. And because of this, these models are sometimes called Wind-Kessel models. Okay, so these are the equations that I just talked about for the components. So you can write up these equations for each component that you have in a circuit. But then you also need to connect the components into a sort of interconnected system of equations. And that you do by another analogy, which is the Kirchhoff's laws. And the Kirchhoff's law of currents is that the ingoing currents into a node equals the outgoing currents. So here we have 2 ingoing and 2 outgoing. So these two and these two has to have the same sum. And this is simply because it's either charged particles or it's blood particles, blood molecules, and they have to simply go somewhere. So if you so because of conservation of mass doesn't disappear, charged particle doesn't disappear or appear. So you simply have to have this conservation. And because of this, if you have this ballooning effect, and this is always a parallel circuit, so you have a sort of current that flows away into that process of the ballooning of the inductor. In the same way, you have Kirchhoff's laws of voltages, or here Kirchhoff's law of pressure drops. So if you look at the pressure drops across each little module here, each little component, and you go around in a circle, so you come back, then by definition you have come back to the same potential again. So all of these delta pressures here, they have to add up to 0, because you are basically going around in a landscape of different pressures. So sometimes you go up, sometimes you go down, but if you come back to the same place, you're at the same place in the landscape, which has the same height. So it simply has to be the same pressure here. But note that typically in at least one of those steps, you go sort of against the direction of the flow, which means that there will be a minus sign almost by definition in one of these flows in order for this to add up to 0. So these two are equations together with the component equations. That's what you need to convert such a circuit diagram to a set of differential algebraic equations. So let's take an example and just make this a little bit more concrete. So here we have some blood flow, and here we have the Wind-Kessel effect, and here we have this inertance, and here we have the resistance. So it's sort of a minimal circuit. You can of course have more compartments, and we'll see an example of that in a little while. So here, for simplicity, we introduce the pressure drops across each of these components, and then we use the equations that we introduced before. So this is the capacitor. This is the voltage differential equation. By the way, for those of you who have seen or will see the Hodgkin-Huxley equation, this is the one for the capacitor across the cell membrane. So then it's actually voltage here. But now we're in flows. So now it's the pressure drop. And which pressure drop? Well, it's the pressure drop across the component that we're looking at, the capacitor. So this is the pressure. And if you want to write it into the standard form of a DIE, then we write it so that we have some expression which is equal to 0. In the same way for the inductor, we just take the standard equation. So remember, the inductor is the one that's resistant to change in flow. So you have a temporary buildup of pressure difference here because you have a change in the flow. And this is the inductance or the inertance. And then we rewrite it to standard form. And the same way for Ohm's law, we write it up. Okay, so these are the 3 equations for the components. So now we have the components. Now we need to bind them together. And we have Kirchhoff's law of voltages, where if we start here and we go in this direction, then here we go against the current, here we go against the current, and here we go with the current. So PR, delta PR and delta PL is with the minus sign, and this is with the plus sign. And notice that we have these ones already here. So these equations sort of bind these 3 together. This one we will have via a differential equation. So by solving this as a differential equation, we get the delta PC. And here, this is just an expression that you actually can replace into here if you sort of want to make it simpler. These are, in a way, auxiliary equations, you could say. Okay, and then we have Kirchhoff's law of currents. And let's look here, for instance. So we have blood flow coming in here. And it's going in 2 directions. It's going down to the Wind-Kessel effect, and it's going through here. So Q in equals QC plus Q out, which means that if we move this to the left-hand side, we have the standard form. So here we have all the standard forms. So these are all the equations for a DIE. So that's how you do it. And again, we could insert these ones here, so we only have this equation, and this equation if we want. But typically a DIE doesn't care about that. As long as the equations are consistent with each other, you can the solver will be happy with either or. And here also in practice, often you drop the deltas, so you just call this PC and you call this PL and you call this PR. Okay, so that's how you do it. Now let's finally look at the slightly bigger example of the actual heart. So here we have a recently published paper in Journal of Physiology, the same journal as the Hodgkin-Huxley papers in the 52, for those who saw the other video. And this is one of the supervisors in the course, Kajsa Tunedal, and Tino Ebbers, her supervisor. And I'm also one of the supervisors to Kajsa. Okay, so here we have a slightly bigger model, but you see it's the same components. This is just that the direction is reversed, and here we have a diode. So this corresponds to a mitral valve, that the blood flow doesn't go backwards. So you can introduce those type of equations as well. But basically here we have the flow through the chambers of the heart and then up through the aortic valve, aorta, and out through the rest of the body. So it's the same type of equations that we saw before, it's just slightly bigger. And then you can fit this model, so you can simulate this model using a DIE solver to data that you collect called 4D flow data. So you put cross-sectional cuts here at different places, so you get time series for the blood flow and these different parts in this blood flow system. And here you see the data in the circles and the simulation with the model in the line. So you see that we can get these quite complicated behaviors with this model here. And we can do this for different patients. And this comes into block 2 when we will estimate parameters. So this is a teaser of block 2, you could say. So we can estimate thus the parameters like the compliance or like the properties that has to do with these different parts of the system. So patient-specific parameters can estimate it by fitting the model to data. And then we can compare different patient groups. So here we can compare people with normal blood pressure, with high blood pressure, and with type 2 diabetes and without type 2 diabetes. And you see that we can see these differences. And this is differences that we can identify because we combine this type of 4-dimensional flow data with this type of model that allows us to estimate parameters in the vessel system that we can't estimate in any other way. So this is sort of just an example of how you can actually use this type of models. And if you want to talk more, or if you want to do an individual project in this direction, then you should talk more to Kajsa, and she can also put you in contact with Tino if you want. Okay, that was it for the lumped parameter models.